In this lecture, we will discuss about some technical terms like distribution factor, rotational stiffness of joint, etc. First, distribution factor. It is defined as the ratio of the moment shared by a member to the applied moment at the joint. That is, dF is equal to mi dash over m. Already we know that m is equal to k theta. Therefore, mi dash is equal to ki theta divided by m sigma k into theta. Theta cancel the same rotation at the joint because of fixed rigidity. Therefore, we get distribution factor is equal to ki, the stiffness factor of that member, over the summation of the stiffnesses of all the members meeting at that joint. That is sigma k. And if we sum up all the distribution factor at a joint, that should be equal to 1. And for cantilever, distribution factor is equal to 0. And the rotational stiffness of joint is defined as the moment required to cause a unique rotation of the joint, which is equal to sigma k, because m is equal to sigma k into theta, but for unit rotation theta is equal to 1, therefore m is equal to sigma k, which is the rotational stiffness of a joint. Okay. So next, relative stiffness, capital K. It is used only for calculation simplification. So when several members meeting at a joint have different support conditions at their other ends, then relative stiffness capital K is used to simplify the computation. If 4 ends of all the members are fixed, then stiffness are same for all members. Therefore, we can cancel the common term such as 4E. Okay, if all the members are of the same material, usually that. So therefore, capital K is equal to I by L. Only the varying, most varying parameters, moment of inertia, that is cross section based on cross section, and the length of the member. So in stiffness we have 4E is the common term, therefore the remaining term is I by L, which is our relative stiffness if 4 ends of all the members are fixed. Next, if we have mixed support conditions, that is semi supported and fixed, then we have to use K, capital K, relative stiffness K, capital K is equal to I by L for fixed support. If the form is fixed, if the form is semi supported, then we have to use 3 by 4 into I by L. Next, carry over moment. When a moment is applied at one end of a member allowing rotation of that end and fixing the far end. Some movement develops at the far end. That movement is called carry-over movement. So this is applicable only if the far end is fixed or interior support. That is the moment carrying capacity, having the moment carrying capacity. If the far end is hinged, then no moment will be carried. And the moment will be carried only in the same direction. Okay? Next, carry-over factor. It is the ratio of carry-over moment to the applied moment. That is COF or CO is equal to M dash over M, where M dash is the carry-over moment or induced moment, M is the applied moment. This carry-over factor is dependent on farther end condition, then variation of I, internal hinge availability, then it takes value either 0 or greater than 1 or less than 1. If further end is pinned or roller, then carry-over factor is equal to 0. That is, the no moment will be carried out because of hinged support or roller support. There is no moment carrying capacity. If the further end is fixed or continuous, that is interior support, then half of the moment will be induced. So that is carry-over factor is equal to half. The extra condition is there should not be any internal hinge. Then if further end is some guided roller, so this is negative, minus 1. That is, moment will induce in the opposite direction. Suppose if we have any internal hinge availability, then the actual carry-over moment will be computed using any method such as column analogy method. If the section is non-prismatic, then also we have to use some methods to find out carrying over factor. Now we will see the steps involved in moment distribution method while solving a problem. So first step is to find out fixed end moments, considering each wheel separately. Next we have to compute distribution factors at each joint, interior joints. So once we have fixed moment and distribution factors, then we can formulate some table, okay, called a distribution table, in which we will do all balance, no carryover factors, carryover process. Okay. So in distribution table we have joints So to consider each joint separately, A, B, C. For example, if this is our beam, then we have A joint, B joint, C joint. The next members, that is under the joint, how many members are meeting at the joint? That's what members. So at joint A, we have only one beam originating from the joint A, that is AB. Therefore, AB. Then at B joint, we have BA as well as BC. Therefore, BA, BC. Similarly, for C joint, we have only CB member. Then we have to write out distribution factors for each member at joints. Okay. Here, in this case, we will have distribution factors here as well as here. There is no need for distribution factors at A and B. Okay. At C. Or, for example, say suppose the joint is hinged support, then distribution factor is 100%. Okay. Sorry, 100%. The carryover is 100%. Then fixed endowment we have to write for each member. So once we have all those things, we have to apply equilibriums at the joints. Okay. So not at fixed end supports, only at hinge or roller end support or hinge support. While balancing, we will do the carryover if the far end is fixed or interior supports. So we have to repeat these two steps, balance and the carryover, till the carryover value is negligible or insignificant. So the last month we have to calculate the final value, adding the vertical, that is values in the vertical column under each member from fixed endowment to the last balance. Okay. That will be the final moment of each. So once we have the final moments, then we can calculate the force, that is the reaction and other things, in order to calculate the shear force by considering the free body diagram of each member. So the last step will be the bending moment diagram and shear force diagram. So in the next video, we will learn how to analyze beams by moment distribution method.